So now, over the course of today, we've developed, first of all, the theory of path independence for integrals. So when are the values of path integrals for a vector field always the same, regardless of how we get from point A to point B, and only caring about what are point A and point B. Those are the path independent integrals. And then we made the leap from path independence to circulation by observing that path-independent vector fields have zero circulation, and also vice versa. We developed a differential measurement of infinitesimal circulation or circulation density called the scalar curl. And then the big finish was Green's theorem. And Green's theorem tells us that we can measure the circulation of any vector field around a simple closed curve as the double integral of the scalar curl on the region that's bounded by that simple closed curve. So here's just a quick summary that pulls together all those different threads before we get an opportunity to do one or two examples to finish everything up for today. So let's say we have a line integral that we're interested in computing. How should we do it? Well, on the one hand, we might say, if my vector field happens to be a gradient of something, then that means that the field is path independent, and we can use the fundamental theorem of line integrals to evaluate it. Just find that scalar potential function and take that function applied to the endpoint minus that function applied to the starting point of my path. And that's all I need to do to compute this line integral. The other path here is if my curve is a simple closed curve. In that case, we can use Green's theorem. And Green's theorem tells us that the circulation, because it is going to be a circulation now because it's a simple closed curve, the circulation around that path is going to equal the double integral over the region that's bounded by that path of the scalar curl with respect to area. And then there's a really special case, and that's when both of these things are simultaneously true. When I both have a gradient vector field, a path-independent vector field, and I have a simple closed curve, well then in that case, we just get a circulation equal to zero, because path-independent vector fields always have zero circulation. So this is kind of the conceptual summary of what we talked about today and how these three different pieces that we did fit together. So to wrap things up for today then, I have an activity 12.7.3, which is the last one in our folder for today. There is a 7.4, but maybe we'll get a chance to talk about that one a little bit later on. It's a little bit less important for us today. But 12.7.3 is going to give us the opportunity to apply Green's theorem to evaluate some circulation integrals. And the circulation integrals that we have to do are given two vector fields, f of x and y and g of x and y, and we're given two different closed paths. One of them is a circle centered at 2, 1 with a radius of 3, and again traversed counterclockwise, because that's the convention that we apply in Green's theorem, because that's what makes scalar curl a positive quantity. And then likewise, in the second part, we have this triangular path starting at the origin, going out to 3, 0, and going up to 3, 3, and then returning back to the origin, again in a counterclockwise orientation. And so to apply Green's theorem to these two cases, we can evaluate the circulation by instead evaluating a double integral of the scalar curl function, where that double integral is taken over the interior, the region that's being bounded by our simple closed curve. So let's wrap things up today by giving you the opportunity to apply Green's theorem by cranking out these double integrals, which is of course going to mean that we have to tape measure our region in some appropriate fashion, and so on and so forth. So all of our double integral skills are going to come back to the table. It may be helpful at some point to use polar coordinates. This one's a little bit nasty because the center of our circle is not at the origin, and so we might need to get a little bit creative when it comes to that one. So we may want to do part B first, because I think that the actual calculus portion of it is going to be a little bit more straightforward than part A. So recapping these two integrals, they ended up being not too terrible, as it turns out. So starting with the second one, we wanted to find the circulation of this vector field around this triangular path. Now, if we were to do the left-hand side of this integral, we would have to set up three different parameterized curves, because we can check that this is not a path-independent vector field. It doesn't pass the screening test, right? And so if we want to do the left-hand side, we have to set up three separate path integrals with three separate parameterizations, one for each side of this triangle, and then crank out f of r of t dotted with r prime of t, yada, yada, yada. That would take a lot of time. So thankfully, we have Green's theorem because we have this closed curve. And so according to Green's theorem, what I can do is find the scalar curl. When I compute the scalar curl of this vector field, it's the x partial derivative of the y component, which gives me 3y, minus the y partial derivative of the x component, which is 2y. Subtract those, I get y. And so what I need is to integrate y over this triangular region, which we pull out a tape measure, and as a type 1 region we can describe as y ranging from 0 to x and x ranging from 0 to 3. And so I need to integrate y with respect to y and then x as an iterated integral. The first step in that iterated integral gives me xy evaluated from y equals, it gives me 1/2, what did I do here? Did I do this step right? I don't think I did. So yeah, we do have 1/2 x squared as the next step of this integral, because you end up getting y squared over 2 evaluated from 0 to x. So that's 1/2 x squared. And then I want an antiderivative for that. And the antiderivative for that is, what's that going to be? 1/6 x cubed evaluated from 0 to 3. And so that's going to be 1/6 of 27. And when I reduce that by 3, I do get 9/2. Ha, funny. So the error that I made led me to the answer 9/2, and doing it the right way also leads us to the answer 9/2. I guess that's the kind of luck that you get when you're a math professor for 15 years. Do it the wrong way and end up with the right answer. No, but you had it right. 9/2 because of this reason. Right, then the first integral. Looking at this one, I was a little bit concerned that our calculus was going to be a nightmare, because we're given a circle whose center is not at the origin, which means that even if we try to use polar coordinates, we would have to get real fancy somehow to evaluate this integral. But you find out right away here that when you take the scalar curl of this vector field, it's the x partial derivative of the second term, which is going to give me 5 plus 2y, minus the y partial derivative of the first component, which is 2y, and the y's cancel, we just get a 5. So this is an example of one, like the preview activity, where the scalar curl ends up just being a constant function. It doesn't depend on x or y, which means that the circulation around any simple closed curve is always going to be the same proportion of the area inside of that curve. So if I took this circle and I moved it around anywhere else in the xy plane, the circulation around that circle would still be the same, because it's proportional to the area of that circle. And we can see that if we plug in now that 5 for our scalar curl on the right-hand side of this Green's theorem evaluation, and then recognize that to evaluate the integral of a constant, we can pull out that constant and just get 5 times the integral of the area. And the area of a circle we can just compute using geometry instead of using calculus. It's pi times the square of the radius. And so pi times 3 squared times 5 gives me a total circulation of 45 pi. So that was a nice example. And again, it's because the vector field was nice enough to have a constant scalar curl that we got away with computing this double integral without having to do any antiderivatives or any calculus at all, just by taking 5 times the area of the disk that we were evaluating. And it's another one of these examples where if we tried to do this path integral according to the left-hand side, right, we would have to parameterize this circle whose center is not at the origin, and so it would have these nasty cosines and sines, +2 and +1 inside of there, and then when we plug that into this vector field, we'd get nasty cosine squareds and cosines times sines, all kinds of nasty stuff that we would have to integrate with respect to t. But doing it this way, we didn't have to do hardly any calculus at all. The only calculus we had to do was the computation of the scalar curl. And then everything after that turned out to be just geometry because the scalar curl was a constant. So Green's theorem really does save the day in a lot of examples whenever we can get away with using it. And we can get away with using it any time we are finding a path integral over a simple closed curve. Just take the scalar curl and evaluate the double integral of the scalar curl instead of evaluating the circulation integral by hand.